This is a story of a unique facility with a daunting name.
The Center for Nanoscale Systems
at Harvard University.
Called CNS for short. It's actually a shared scientific resource containing various labs and nests of high-tech devices, many the best of their kind.
There are only 2 or 3 of these microscopes in the world.
CNS's multifaceted array of scientific instrumentation is primarily housed along 2 floors in this long building and includes a fully outfitted clean room, a laser lab, and an alphabet soup of microscopes.
SEM, cryo-SEM,
the LEAM,
and TEM,
focused ion beam,
atom probe,
and more. Between them, these machines can image just about anything.
How many atoms did you get in this needle total?
130 million atoms, so nice and healthy data set.
Despite the sophistication of all the instrumentation here, CNS is basically a self-use facility.
Keep iterating that process until we get it exactly where we want it to be.
Where its staff trains researchers how to operate these costly devices themselves, something that is extremely valuable for Harvard faculty and students.
Very high atomic resolution.
So CNS has been super helpful for me in how I work with undergraduates. They allow undergraduates to access these cutting-edge instruments that ordinarily would be inaccessible to students of that age. But my undergraduates are really able to do cutting-edge work on these instruments because of the educational outreach mission of CNS.
Training is only part of what CNS does.
It's too hot, the material breaks down or melts.
Its resources and expert staff make it invaluable to researchers from industry as well as academia, including researchers from non-Harvard colleges and universities.
We have a wide variety of folks from other academic institutions that don't necessarily have access to the resources that we have here, and we open our doors to them.
And those doors stay open 24 hours a day. From developing new materials to making prototypes for next-generation devices, CNS has been the starting point for an extraordinary number of scientific careers.
Very hard to imagine my professional life, my career without CNS.
In this work, we have 2 college centers.
CNS is a one-stop shop. You can come in and fabricate something, you can characterize it, you can image it, and we are completely staffed with experts that will help you do your work.
And demonstrate a 2D and 3D surface reconstruction.
That's what a core facility is about. You have a centralized place where skilled people can work with complicated instruments and provide great data for people that need it.
Hello, Jim speaking.
To access CNS facilities, you must begin with this man.
Hi, Jim Reynolds here. Hello, Jim speaking.
Jim Reynolds is CNS's gatekeeper, record keeper, and traffic cop.
Jim?
Yes.
I was wondering...
Applicants fill out forms describing their research needs, and Reynolds takes it from there.
My job is to assist folks in making sure that they end up with the right members of our technical staff to get the training on the instrumentation that will make their project successful. I'm the beginning of their journey.
The biggest user groups at CNS are from engineering and applied sciences, closely followed by physics, chemistry, and chemical biology. But there are unique users as well.
This peak right here, which you'll see is hanging out.
Stephen Parman is a geochemist from Brown University. He and his postdoc Tom Williams have come to CNS with very rare samples that need analyzing. Samples that came from the moon.
So the samples we're analyzing today are from the Apollo 17 mission that the astronauts found on the ground. It turned out to be a volcanic deposit of these little volcanic glass beads, almost like an ash.
You can't see the beads because they're housed inside this vacuum-sealed container.
There are a lot of materials out there that can't tolerate the conditions of Earth at all. They can't tolerate oxygen, moisture, ultraviolet light, even the smallest speck of dust, anything like that. It will ruin the material and it'll ruin your experiment. So we flood this little airlock with dry nitrogen just to keep everything clean. So we've had to create an ecosystem of interconnected tools where you can take materials back and forth without exposing them to anything.
Inside a vacuum chamber and under extreme atomic magnification, a moon bead looks like this.
Slight adjustments, but looks good.
The researchers want to know the precise makeup and distribution of elements on the early moon. And trapped inside the beads are samples of those early elements from billions of years ago. But retrieving them is extremely difficult.
All right, so we'll get that lined up here. That makes sense.
So the team will need to rely on Austin's skill for the initial effort.
At Brown, we have some tools like SEMs and TEMs, but we don't have Austin.
And with Austin's help, they just might get answers to a puzzling mystery.
And the leading theory for how the moon was formed is called the giant impact hypothesis. This kind of Mars-sized object hits the Earth, it kind of shatters it. All this debris goes in orbit around the Earth.
And this red-hot maelstrom eventually congeals and forms the moon. Or so the theory goes. But the samples may tell another story, because a volcanic deposit of glass beads doesn't fit the impact theory.
When you run all the models of this impact, it heats everything up so much you would think it would just drive off all the volatiles. By understanding what volatiles are there, we're trying to make these two kind of contradictory lines of evidence fit, the giant impact with the volatiles still being present in the moon.
The first step is to take one of the beads from the sample and sculpt the surface, leaving a finger of material to analyze, something Austin has already done with the ion beam microscope.
And now we're going to reach in, we're going to grab the free end with our micromanipulator, and we're going to cut off the attached end, and then we can pull this whole piece right out.
But everything is so small, they realize they have to make adjustments or they might wreck the sample. After sculpting it a bit more to better isolate the finger, they are ready.
And we're just going to do what's called lift out. And this is always a little exciting because you never know quite what's going to happen, but here we go.
And off it goes.
A couple femtograms of lunar sample.
After milling the sample to a needle-like shape, it goes to the atom probe room where this extraordinary device can chemically identify every atom in the sample. Since the experiment was a first, there's no guarantee that it would work. But the results were stunning.
Every dot on the screen, every one of these dots is an individual atom, and they've all been color-coded according to which element they are.
It's incredible that you can see that.
I know, right?
How many atoms did you get in this needle total?
This needle is 130 million atoms. Yeah, they're all there. A whole bunch of stuff, various silicon and silicon oxides, and then the zinc sulfide. So nice and healthy data set.
We got the first successful atom probe data on these condensates that anyone's ever gotten.
Despite the work ahead, this was a major step for understanding the geology and evolution of the early moon. And Austin is now training Tom Williams to operate the atom probe on his own.
I was also a user of this facility for a couple of years, and now I train others. It's tremendously satisfying anytime the work I do helps someone learn something they couldn't have learned otherwise. Hydride double plus.
I think Harvard has done a good job of hiring staff who are themselves curious scientists, and those curious scientists are really interested in pushing the boundaries of what they can do with their instrumentation. And I think they really consider themselves still to be scientists, not just technicians.
If we scan back and forth, you can see that everything's growing nicely.
In reality, the most important piece of equipment in our building is our people. Training is what we do.
The clean room is the busiest facility at CNS, and in many respects, it's most essential. Users don bunny suits to prevent experiments from being exposed to contaminants. Here, beginners learning the basics for fabricating nanoscale devices work right next to advanced users, developing an array of electrical and photonic prototypes. Although many of these tiny devices are etched or printed on chips, this is not a chip-making lab.
The way I described it sometimes is that we're the most sophisticated experimental clean room fabrication facility in the world. If you want to make a 16-layer microprocessor, you go to Intel. If you want to turn a butterfly's butt into a transistor, you go to a developmental fab.
We have users who are working on small chips. We also have users who are...
Mukesh Khan was once a first-year student, just like the beginners he's mentoring now.
So there are pros and cons between this type of technique and method they use, and depending again on your end application. We are introducing them to different tools, capabilities that we have, and then how can they get the most out of these tools and capabilities in order so that they can go and do their own research.
How should I determine which tool to use?
There are two ways. One is like what kind of device you're making, and from that we can figure out what quality of oxide would work for you.
But getting users trained up in all the processes here is neither quick nor easy.
We'll start by positioning it in the center, which is considered the D position.
So to become clean room qualified, users who are interested in fabrication have to go through 5 or 6 steps before they actually touch the final instrument that they need as part of their fabrication.
Adjust the cantilever oscillation until it's at an amplitude of 1 volt.
But most students do get qualified, and many will go on to careers in the sciences, something that makes Mukesh proud.
So on a personal level, the way I find working at CNS very satisfying is that you are enabling high quality research and that you're also training the next generation of workforce. So it's very crucial that we transfer our experience and knowledge to all the young researchers who are getting trained and working in a place like Harvard.
I think the most useful thing really is having students who are trained to keep searching. They're not going to give up if the first few tries fail. That confidence and that persistence and that willingness to keep looking for the right tool to do the job, that's probably the most valuable aspect of workforce development that CNS allows us to do here at Harvard.
I was looking at the code that you had up there and I was like, this is pretty much there.
Rob Devlin was once one of those bunny-suited beginners learning the ropes at CNS. After several years in Federico Capasso's lab at Harvard, today he is the CEO of MetaLens, a unique optical device company in Boston that he and Capasso founded.
CNS has been critical to MetaLens getting where MetaLens is today.
And where that is making next-generation optical devices developed in large part at CNS.
What we're trying to do at MetaLens is change cameras, change imaging, change sensing. And what that means is, if you look at cameras we're using right now, there are a bunch of really big, bulky lenses and optics that make this thing so big. Why is that the case? Because normally to make high-definition images, you need a lot of big, bulky lenses. So we came up with this concept of the metasurface, or MetaLens, and what that is a way to take all of these big, bulky, curved optics and shrink them down to sort of nanoscale dimensions.
Cell phones and computers already have tiny lenses, but MetaLens lenses are much smaller and far more versatile. But how does a lens that is nanoscale tiny and flat actually work?
If you were to zoom in on one of our metasurface chips, what you'll see are tens of millions of cylindrical pillars, a fraction of the width of a human hair.
The entire array can respond to and interact with the light passing through the metasurface because the pillars act like antennas. and the team can configure the pillars to analyze the light striking them in order to perform a myriad number of tasks, something that takes a lot of testing.
What we have here is a measurement setup to make sure the lens performs as well as we designed it to work.
Junsa Park has mounted a glass chip etched with billions of meta-lenses in front of a laser light source emanating from this tube.
All this rainbow colored area is all those billions of nanostructures etched into the glass.
If the meta-lenses are working as designed, they will focus the light to a specific predetermined point. You can't see the laser light until Junsa puts a card in front of the lens array.
You can see that the light will defocus, come to a focus, and defocus again.
A camera device opposite the array then measures the focus point.
So this is the final step where we characterize the lens and see if our design and theory were correct.
Every design task is measured this way, and there are a myriad number of tasks MetaLens can perform, like capturing minute details for enhanced facial recognition.
It's really anywhere that optics can go. And because of these meta surfaces, we're able to put this into cell phones because it's now small enough. It's now cheap enough for that type of mass market.
And perhaps most importantly for a mass market,
what you can do with a meta surface is actually print this like you're printing computer chips now. You can print something like 10,000 lenses on a single one of these wafers. This meant that we were able to go from selling 0 units to selling millions of units because we were using these existing semiconductor foundries.
And the prospects for the company.
When we published a paper that ended up on the cover of Science, we started getting calls from some of the biggest cell phone manufacturers to put them into real-world devices.
So after years of development and with support of CNS, it looks like MetaLens is facing a bright future indeed. And they're far from finished with CNS.
So anytime we have a new idea, anytime we have a new concept, CNS is the first stop.
So I've seen many of the people here start spin-off companies based on techniques or devices that they have created here, and it's very satisfying to know that you had some small role in their success.
So CNS has been really open to introducing new materials and also developing new fabrication technologies. We don't do push-button cookie cutter recipes, we develop our own recipes. This allows you really to kind of push frontiers of science and technology. So without CNS, it would be impossible to do this work.
I think that Harvard has always understood that the goal of this infrastructure that was created at CNS is to provide an environment so somebody can win a Nobel Prize in our building.